Hello, my name is Foroogh Shamsi. I am a postdoc from EC Department of Rutgers University, working at the Integrated Systems and Neuroimaging Lab under the supervision of Professor Najafizadeh. I am presenting our work titled Recognizing Pain in Motor Imagery EEG Recordings Using Dynamic Functional Connectivity Graphs. And I would like to acknowledge the NSF support for this project. Here is the outline of my talk. I will start my talk with an introduction about the problem and the motivation for this work. Then I will explain the experimental design and data analysis. After that, I will present the results, and finally, I will conclude the talk. A BCI system converts brain signals corresponding to different motor imagery or cognitive tasks into control commands to operate an external device such as a prosthetic hand, a wheelchair, or a robotic arm. EEG is the most used non-invasive neuroimaging technique in BCI since it is a low-cost and easy-to-use method to monitor brain activities with an excellent temporal resolution. BCI technology can establish a communication way for patients with severe motor disabilities, such as patients with high spinal cord injury, stroke, or ALS. Therefore, an accurate decoding or classification of brain signals is very important to ensure the safety of the users. Pain is unfortunately a common problem in a large group of patients who are in real need for BCI-based assistive technologies. On the other hand, previous studies indicated that the presence of the pain affects brain activities. Results of these studies, along with the prevalence of the pain in patients in need of the BCI technology, suggest the importance of considering this issue in the development of BCIs. In other words, BCIs designed for these patients should be adapted to take the pain condition into account. This issue motivates for investigating whether the pain can be recognized in BCIs. Previous studies on classification of pain using EEG can be categorized into two groups of discriminating pain versus no pain conditions and differentiation of different levels of pain. In studies that worked on discriminating pain versus no pain condition, the pain was induced while the subjects were on resting states. However, in this study, we focused on discriminating pain versus no pain condition in a task-based framework, where the subjects perform motor imagery tasks in a pain-free and pain condition. Now I will explain the experimental design and data analysis methods. The experimental setup we use for data collection is from brain products and recorded EEG data from 32 channels and with a sampling rate of 500 Hz. The channel configuration is shown in this picture. And to induce pain, we applied heat to the subject's skin. PSA2 device pomada with a 30 by 30 square millimeter standard thermode was used, and the pain was applied on the dorsum of subject's left hands. Prior to the experiment, subjects' pain threshold and tolerance temperatures were measured in a screening session. To determine their pain threshold, we slowly increased the temperature of the thermode and asked the subjects to press the button on a response unit to indicate the moment that the temperature became painful to them. And for the tolerance measurement, they were instructed to press the button when the pain became intolerable. Each trials of each measurement were performed by the subjects, and the average temperatures from each measurement when considered as the threshold and tolerance temperatures. The mean of the threshold and tolerance temperatures was calculated, and during the experiment, the temperature of the thermode was set to a random number between Tp plus and -1 in order to induce pain. And in order to avoid habituation to the heat, the location of the thermode was slightly moved on subject's hand for different blocks of the experiment. We recruited 4 healthy and right-handed subjects and 12 no pain and pain experiment blocks, 6 of each with random order were performed by the subjects. 4 motor imagery tests were considered, including right hand, left hand, foot, and tongue movement imageries. Each block of the experiment started with a 10-second of initial fixation. And at the beginning of each trial, an arrow indicating the type of motor imagery task was displayed for 1 second on the screen. Next, a diamond symbol was displayed for 3 seconds. Subjects were instructed to start the imagery task as soon as they saw the diamond symbol until it was disappeared from the screen. And this was followed by a 2 to 4 second inter-trial rest. For pain blocks, the thermal temperature was set to the stimulus temperature that we calculated before, and for no pain blocks, it was set to the baseline temperature, which was 32 Celsius. And 72 trials of each class were recorded under pain and no pain conditions. After collecting the data, the goal was to use EEG recordings to differentiate different pain-free versus pain motor imagery tasks. To achieve this goal, we followed 4 steps. The data analysis started with the pre-processing of the raw data. Different steps of pre-processing include bandpass filtering, baseline correction, and artifact removal using ICA. In this study, we aim to investigate the significance of different EEG bands in differentiation of pain versus no pain motor imagery tasks. Therefore, for band-specific analysis, we decomposed EEG data into 5 subbands of delta, theta, alpha, beta, and gamma using stationary wavelet transform. And this step was skipped for the analysis of undecomposed data. The pre-processed and decomposed data was passed to the feature extraction step. First, the data was segmented into time intervals during which the spatial distribution of functional connectivity networks were quasi-stationary. We employed a recently proposed SVD-based segmentation method, which is called source-informed segmentation, to identify the segment boundaries. Then for each identified segment, the corresponding functional connectivity graphs was constructed and converted to vector formats. The vectorized graphs are considered as the features for the classification problem. To take the advantage of the information in the extracted features as well as their temporal structure, we employed a long short-term memory or LSTM classifier, and the structure of the LSTM network is shown in this figure. 70% of the data was used for training, 15% for cross-validation, and 15% for testing the classifier. Now I will present and discuss the results. Here are the classification results for all subjects using all bands without decomposing into different bands. Different columns show the classification accuracy for discriminating different motor imagery tasks performed under pain-free versus pain conditions. For example, the right-hand column shows the results of classification between right-hand motor imagery without pain versus right-hand motor imagery with pain. Average classification accuracy of around 79% was achieved across the subjects and tasks. These results suggest that the proposed method based on dynamic functional connectivity graphs can accurately differentiate various pain-free motor imagery tasks from their corresponding tasks with added pain. Therefore, this method can serve as a reliable predictor to determine whether the motor imagery tasks are performed in pain-free or under pain conditions. Now, for the band-specific discrimination, the average classification accuracies from different bands are shown in this bar graph. Our results suggest that using the gamma band, the average classification accuracy of 84% can be achieved across tasks and subjects, which is even higher than the case of using the undecomposed data. On the other hand, using delta and theta bands, the average classification accuracy is around 50%, which is the chance level. These results indicate the relevance of the gamma band in discrimination of motor imagery tasks under pain-free versus pain condition using dynamic functional connectivity graphs. Now I will conclude the talk by some points. Classification results indicated the effectiveness of our proposed functional connectivity-based method in differentiation of motor imagery tasks performed under pain-free versus pain conditions. And also our results using different frequency bands suggest that gamma band offers the highest average accuracy for this classification problem. And also, delta and theta bands do not seem to provide discriminatory information between pain-free and pain conditions. And for our future work, we plan to develop motor imagery-based BCI algorithms which incorporate the pain detection capability and can adapt to the pain condition without affecting the classification performance. And thank you for your attention. If you have any question, please feel free to contact us.